All right, in the last video I showed you basically how to make a new truth table with the answer set for different problems and determine whether this equation is equivalent to the solution set that they have. Keeping in mind that you would have to do that multiple times. So when you come over here, you'd have to do that, in this case, maybe as many as 5 times, or until you found which one of these satisfies this equation. But let me show you something else, and that is that you can determine the equation that you want just by looking at just this much. What you want to do is you want to look at what's called the min terms. The min terms are all the times when the answer is 1. So in here we have 3 different min terms. And we can describe this truth table as being true whenever A and B is true, or when A is true and B is false, or when A is false and B is false. And we don't even bother with this one. We don't care when it's false. We only care about when it's true, when you know, because whenever we deal with an if statement, it only triggers when the statement is true. When it's false, it completely ignores it. So we really don't care about the 0 here. We just care about these times when the statement is true. Well, if you listened carefully to what I said before, this statement is true when A and B is true, or when A is true and B is false, or when A is false and B is false. So let's write that down. It's true when A and B is true, or when A is true and B is not true, this one, or, I'm going to run out of room here, when A is false and B is false, not A and not B. Cross this off so you don't get confused with what I'm doing here. So this is the statement right here. Unfortunately, that matches up with none of our statements over here. And that's because this statement here has been simplified to match one of these statements. So what you have to do is you have to use your Boolean logic in order to convert this statement right here into one of these statements right here. Well, that's where, like I said, your Boolean logic comes into play. And I don't teach Boolean logic using ands and ors like this, because with the computer science, I would just have you just put it in just like this. It doesn't cost anything, it just takes longer to type, and it's not a big deal. But if we're doing electronics, I would have you simplify this, because for every time you see an and or an or, and every time you see an A or B, it's another wire. And when you're talking about wires, there is cost associated with that. There's mistakes that can be made. There's soldering joints that can be get mucked up. So we would want to simplify this as much as possible. With computer science, I would accept this. With electronics, I would definitely not accept that. That's way too complex. So we're going to use the things I mentioned in my other video. We're going to use plus and multiplication. Addition is or, multiplication is and. So all we have to do is replace these with these two symbols. So when it says A and B, we actually don't use the multiplication. We just have A and B, like that, or A and not B, or not A and B. So A, not B, not, like that. So now we've gotten a whole new thing here. And if we look online, let's see if I can get another screen going. And I'm just going to type in Boolean laws and theorems PDF. Let's see what this gives me. Usually these are pretty standard. So yeah, I think I've went over these in a couple other videos. These are all the laws that you can use in Boolean logic, and I would I would ask that you actually study them. They're not difficult to learn, but you just have to know that like a double negative on an x is just a regular x. X plus 0 is x. X plus 1 is just 1. So what this means is, like, just to save you maybe a little bit of time here, let's take this one. This is x or 1. 1, remember, is true. Well, in this case, x or true is always going to be true, because it doesn't matter if x is true or false. Because the other one is true, this whole statement is always going to be true. For example, on this one here, x or x. Well, if x is true or x is true, then the whole statement is going to be true. So it depends on what x is, doesn't it? So if this one is false and this one is false, then this must be false. So if this one is true, this one can't be false because they're both x. So if this is true, this has to be true. If that's true and that's true, that has to be true. So you can kind of see how they come up with this logic here. And you might want to work your way through this. Remember right here, this is and. These are the and laws. I told you multiplication, that's what the little dot is. It means and. But the one that I want to show you, though, is there's commutative and associative and distributive. And there's also the simplification laws here. So there's also De Morgan's laws. This is a very handy one. I can even show you how to use that one here in a second. But let's get back to where we were. So let's see if I can use some Boolean logic to solve this problem. Here I'm just going to solve this part right here. I'm going to ignore this for right now. I'm going to factor out an a. So a is b or b not. The line over the b, by the way, means not. Or a, b. This part here, well, let's look at our laws. What does that do to us? It says here, if I have an x or an x naught, that equals 1. Okay. So this is a x or x naught, or b naught in this case. So I know that this is equal to 1. So it's going to be a 1 or a naught b naught. So if I have an a, whoops, if I have an a and a 1, what does that give me? Let's look at our laws here. If I have an x or a 1, that equals x. So I'm going to apply that here. That means if I have an a or 1, that must just be a or a naught b naught. All right, well, I'll give you a little hint. We've already reached our answer. There's some more simplification that can go along here, but this actually already matches one of the things that we had in our answer thing, in our answers here. It's one of these down here. Let me convert this now to computer logic, and you're just going to do what we did up here but backwards. So it's going to be a, and an and is an or statement, and then it's going to be a naught b naught. It's going to do a so let's see, I think that matches one of them. Yeah, right here. Right there. So I'm going to assume that that's going to be my answer. Now, to work this out for sure, what I'd want to do is I'd want to take this and put it back into my truth table to make sure that's going to work. So let's go ahead and do that. So I'm going to take this here and put it back into my truth table. It's going to be kind of hard. The first thing I'm going to do is I'm going to have a not a and a not b here. I already have a not a and a not b here. I'm going to AND these together, so it's going to be a not and b not. So I'm going to AND those two together. 0, 0, 0, 1. Did I do that right? 0, 0, 0, 1, because that's an AND statement. And now I need to OR that with a here. Oops. Yeah. Whoops. Need to OR that with my a right down there. So I'm going to take this statement here. It's going to be a OR. Sorry about my handwriting, it's getting a little cramped down here. Remember, I'm just checking to see if this becomes my solution set right here. So this and this part here, which is this, with A is way over here. So this should be a 1, 1 and a 0 is a 1, a 0 and a 0 is a 0, a 0 and a 1 is a 1, which does actually match up with my solution set. So I know that this is the correct answer, and actually I didn't even, to come up with this, I didn't even bother making a truth table, did I? I just used Boolean logic that went from basically from here all the way down. Okay, looks like my video froze for a little bit, but here I found my answer. Basically was what I was telling you is I found my answer just by using Boolean logic. I found my min terms, I put them right here, right? I converted that into something that I like to work with. I like to use addition and multiplication. I used some of my Boolean theorems, and I came up with my answer, and then I come up with my ultimate answer down here. Now, I will say that even in electronics, I would not accept this either, because this is not the most simplified answer. So I don't like how they did this, because there's a much simpler way to express this thing right here. If we look at our basic laws of theorems here, right here, if we have an x or a x not y, that simplifies down to x or y, and we can use that right over, we can use that right over here, because this will simplify down to a or b not. So ultimately we can make this even a lot simpler than what they have. If you want to do this a different way, this is just for if you want to get a little bit more advanced with it and you're interested in Boolean logic, and I think you should look into it. I'm going to show you a third way here. If you noticed, we found the min terms of these things. Another way you can solve this is by finding the, I can't remember if that's actually called the max term or not, but I'm going to use this 1, but I'm going to find the negation of that. So this equation, this truth table is equivalent to this equation, but it is also equivalent to the opposite of, let me write this one down here. This is going to be a naught, I'm going to write it down like this, and b, and that's what this is. If it were a min term, it's not a min term, it's a zero term. Again, I can't remember if that's called a max term or not, but it's the opposite of this whole thing should be equivalent to this solution set. This is kind of an advanced thing that I'm looking at here, but then I can use De Morgan's law, and I can split this and change the function that's inside here. So it should be a not not and b not. A not not is the same thing as a or b not, which is exactly what I got before. This is just a little quicker way to solve this equation, and it's kind of, like I said, a little bit more advanced. But I guess what I'm saying is that there are other ways to solve truth tables that will get you some more simplified logic. Again, I'm thinking computer science, I would just accept this, but for electronics, I would not accept this. And then I wouldn't even accept this answer. I would make you go back and simplify it even more. And then I would probably give people extra credit if they knew to solve it this way. This is a lot quicker way to solve it. And I don't know if it could be even a lot more accurate because you're only dealing with one term at this point. So, well, I hope that helps. Again, if you ever get a